Welcome, everybody, to your free GMAT Prep Hour. It is August 6, 2023. I will be your host through the wonderful world of the GMAT tonight. My name is Reed Arnold. Welcome, everybody, here live. And if you are watching in the future on YouTube, welcome from YouTube. Quick note here, we do have other free options available to you for those of you trying to study on the cheap. You can try any of our first GMAT classes free of charge. That's actually 11% of our course that you don't have to pay for. I always tell people you might as well go to that even if you have no intention of signing up. It's a free course. We talk about some big stuff in that first day. It's just general study tips, how the test works, how data sufficiency works, one of the major GMAT question types that you want to be aware of. A lot of times we talk about sentence correction, so you want to go to that first class even if you don't intend on going to any of the others. You can also try a similar thing. You can try a sample of our self-paced study kit using our Interact video program, give you a taste of how that program works and covers much of the same material as that first class. We also have our Foundations of GMAT Math workshops that are completely free. There are 2 a month. Usually we have 2 going on right now, the Foundations of Math Computations and the Foundations of Math Variables. About 5, they're 2 5-hour courses, doesn't matter what order you take them in. Hope to see you at one of those coming up soon. There's also these free GMAT prep hours. We record them, we put them on YouTube. There's a whole library of free prep hours at this point. And honestly, anything you need to study, we probably have a video on it. You could basically make your own course syllabus out of the free prep hours we have. So take advantage of those if you're looking to study. Before we jump in and before I reveal what today's question or what today's topic is, I'm going to throw you to the wolves. But before I do that, I'm going to give you a quick crash course on data sufficiency because today's lesson is focused on data sufficiency. And we want to make sure we have the basics of how that works. Again, if you are just starting to study, this is one of the biggest things to get used to early. It's a very weird GMAT specific question type. Go ahead, take 30 seconds just to look over this question here. Don't try to do it or anything. We're just going to talk about how this question type works. All right, so again, this is going to be a little bit fast for those of you that are just jumping into this. But in fact, I would say if you're watching this recording and you don't know how data sufficiency works, I would pause, go investigate that for a while before you continue. But for those of you that have seen it, just need a little brush up. Remember, you're going to be asked a question. And it's going to look like a kind of a typical standardized test math problem, usually. You're then going to get 2 statements adding additional information to that problem, and then you're going to get these 5 answer choices. And the thing that's different about data sufficiency is that we aren't technically trying to answer the question that is asked. We are trying to say where in these 2 statements is there enough information to answer the question that is asked. So in this particular situation here, statement 1 does not give me enough information to say how many employees were senior managers. So statement 1 is not sufficient, which means I can get rid of any answer that says statement 1 is sufficient, which would be A and D. I could then look at statement 2 and it tells me that 64 were not senior managers, but that's not enough to know how many were senior managers. So statement 2 is insufficient. I can get rid of anything that says statement 2 is statement 2 is insufficient. I can get rid of any answer that says statement 2 is sufficient. So I can get rid of answer B and also D, technically, although I've already gotten rid of D. Now I'm down between C and E. And in this case, the 2 together are sufficient, but not alone. Because if I know 80% were senior managers and 64 were not, I have enough information to figure out how many were. I don't actually need to do it, though. That's the difference between data sufficiency and other test prep questions or test questions. Usually you have to get to the answer. Here, I just know that I could get to the answer, and that's enough. So I would choose C and be done with this question. So that's how data sufficiency works. Again, a very quick refresher or crash course. But today's lesson is going to be focused on this particular question type. So I'm going to throw you to a significantly harder data sufficiency question here to introduce the topic we will discuss tonight. Take 2 minutes. That is the test average for quant problems on the GMAT. Take 2 minutes to try to answer this question here. All right, that is 2 minutes. So if you have an answer, go ahead and send it in the chat. If it's a guess, put a question mark by it. That's fine. If you're at home and you think you could get it with a little more time, go ahead and try. But you don't want to let yourself go too long without choosing an answer on this test. When you're practicing, you want to get used to the GMAT pace. And there are times you're going to have to guess and move on. So before we take a look at the answer to this question, I'm going to introduce the topic. Today's lesson is on testing cases, one of the most important GMAT strategies out there. You want to become a master at this strategy. You want to know it backwards and forwards. I've started to go like, I become a lunatic in class talking about testing cases because I'm so emphatic with my students about, getting it down, make sure you know how it works, practice, practice, practice. We have 2 other free prep hours already on testing cases, one that I made, one made by Wit. They're both great lessons, rehash introductions, whatever you want. They will guide you through how testing cases works and why it works and why you want to be good at it. Today, we're going to talk about the common traps and errors that people either step into or make when they are testing cases. We're going to talk about how testing cases and when and why it goes wrong. And for this particular question, this is one of the most common testing cases errors I see. Students don't test cases at all. That's one of the first and most important errors to talk about with testing cases is, did you even test cases? And so if I'm seeing this question, I'm doing this question, I'd say, okay, so there's 30 to 50 students in this situation. They're in red or blue group. I want to know the total. That's the question. What is the total? I go to statement 1. It tells me that there are 60%. And then maybe I'd put like 1.6 blue equals red if I'm doing an algebraic translation of that equation. 60% more students in the red group than in the blue group. Take the blue group, increase it by 60%. That's the red group. I want to know the total. And, okay, 60% more, but that's not enough, right? Because there's not enough information in that situation. That just gives me a 60% comparison. And I don't know if, what the actual values are. So I would say insufficient, and I would be wrong. If you said this was insufficient in kind of the reasoning I just laid out, like, that doesn't seem like enough, you have stepped into one of the most important testing cases trap there is, which is to not test cases to prove your gut instincts. The GMAT is very good at making things that seem insufficient be sufficient, and vice versa. They're very good at making things that seem sufficient be insufficient. And so you want to make sure you can prove your impulses by the process of testing cases and actually show this thing is in fact insufficient. And here's why this first statement is in fact sufficient. And it has to do with this limit, this 30 to 50 student limit. If I have 60% more students in the red group than the blue group, I might think about some cases that fit that rule. So I could make, well, let's see, percentages, right? They work nice with 100 and 10. So let's say that there are 10 in the blue group, there would be 16 in the red group. The total would be 26. Well, hold up though. That actually doesn't work because it needs to be a minimum of 30 in the class. And so this number actually is not going to work. I can actually get rid of this case because it breaks a rule. All right, let's think of another case that would work with this. Well, I could divide by 2. The easiest would be 5 to 8. Again, that was going to be too small, so I wouldn't use that. But this is actually a good starting point because from here I can scale up this ratio. In fact, 60% more means a ratio of 5 to 8. So it could be 5 to 8, 10 to 16. We've already gotten rid of that. It could be 15 to 24, though. I could multiply by 3, and then the total is 39. So that's a possibility. Then I could multiply by 4, and it could be 20 and 32, and that's 52. But that's also, now that's too big. 50 is the maximum. I'm actually too big. So the only numbers that actually fit this percentage in this range are 15 and 24. Sneaky, sneaky GMAT. And so statement 1 is actually sufficient here. And I could prove that just by laying out cases that fit a 60% ratio, 60% comparison in the range 30 to 50 students. Statement 2 tells me there are 24 in the red group. But without statement 1's information, that's not going to be sufficient. What is blue? I have to take this statement on its own. I can't use this information anymore. So what is blue? I don't know. The answer here is A. That first mistake, though, that first big mistake to know is that you should test cases to prove your gut impulse right. Sometimes you will be right. Sometimes your gut impulse will be right, but there are many times you'll catch a mistake. You'll catch the GMATs doing something sneaky just by going through the process to test cases. And even if you end up proving your gut impulse, you prove your gut impulse right, often the testing cases you did there will help unveil something about the question that is useful. So you should just make sure you do a little bit of work, even when you think you know the outcome. Go ahead, test some cases to show your gut impulse is true. In fact, if you're ever in doubt of what to do at all, if you're ever on a data sufficiency question, you're just like, I don't know what to do, throw a case down that follows the rules. Just have that be the first thing you do. Throw a case down that follows the rules, see what it tells you, see if you figure anything out. However, today I am less interested in this particular kind of mistake. It's a big one. You do want to make sure you are testing cases to prove your impulse is right or wrong about a statement or the statement's sufficiency. But I'm going to be more interested in the kinds of errors that happen when you are testing cases, when you're actually in the game and you're like, I'm going to test cases, I'm going to throw cases down. How then do we go awry in the testing cases process? Well, the first thing I want to lay out that is true is that in data sufficiency, in a data sufficiency question, there are two kinds of errors you can make, similar to two kinds of errors you might make in statistics. There's type 1 and type 2 errors that can be made in data sufficiency. A type 1 error is when you decide that a situation, the statement you're dealing with, or if it's time to take the two statements together, if you decide that there is enough information to answer the question that is asked, but there actually is not. That is a type 1 error. A type 2 error is the opposite. It's when you're looking at the situation and you decide that there is not enough information to answer the question, but there is. And one thing I highly encourage you to do as you're studying is to, when you're working data sufficiency, to choose a letter and then check your answer. And without going to the explanation, just first categorize what kind of error you made. Did you make a type 1 or a type 2 error? Or sometimes you can actually make both at once. And then look at how that error might have been made. And we're going to go through some of the common things that happen when people make a type 1 or a type 2 error. Have this video in mind and run through the list. Did I assume something that wasn't given? Did I forget a rule that was given? Did I mistake the testing cases process? We'll clarify how that works, but keep in mind what kind of error you made. And so I've made this little table here. If the right answer is A, B, C, D, or E, and you chose A, B, C, D, or E, what kind of error did you make? And of course, if you're on the diagonal, you got the right answer, right? If you choose the right letter, you're good to go. Now make sure you got it right for good reasons. But if you choose, for instance, if you choose answer, let's do a simple one, right? If you choose A, but the right answer was C, you have made a type 1 error because you said by choosing A that statement 1 was sufficient on its own. But when the right answer is C, statement 1 is actually not sufficient on its own. So you're saying statement 1 is sufficient when it is not. That is a type 1 error. Conversely, if you choose, for instance, if you choose B when the right answer was D, you have made a type 2 error. You were correct on statement 2. Statement 2 was sufficient. But you said statement 1 was not sufficient on its own, and it was. So you made a type 2 error. And notice there are a few times when you make both errors at once. If you choose A and the right answer is B, or if you choose B and the right answer is A, you are making both errors at once. You're saying a statement is sufficient when it's not, and you're saying the other sufficient statement is not sufficient when it is. So you're making both errors at once in that instance. And actually, there's one type here, down here, when you choose E, and if the answer is A, B, or D, you're making several type 2 errors. If the right answer is A and you choose E, well, you said that statement 1 was not sufficient on its own, but it was. So that's a type 1 error. You're also saying statement 1 and 2 together were not sufficient. But if statement 1 is sufficient on its own, you're also missing something at that C level as well. So you kind of make two type 2 errors about that first statement. And if the answer is D and you choose E, you're making a lot of type 2 errors, because you're saying neither statement is sufficient on its own, and you're saying it's not sufficient when they're together, but actually it's been enough the whole time. So you kind of make 3 type 2 errors in that instance. From our data, based on how we know students answer tests and OG questions, we really think that type 2 errors are the more common kind of mistake. It is a little more common for people to say a situation is not sufficient when it is sufficient than it is for students to say a statement is sufficient when it's not. Type 2 errors are a little more common, and partially that's because people don't test cases. That's really the big reason why type 2 errors are more prevalent, is because people just don't prove their instincts right, and their instincts are wrong. And if they tested cases, they would realize their instincts are wrong. By the way, nothing wrong with having bad instincts. The test is very good at tricking instincts, even people who are good at the test. I cannot tell you how many times I've been doing a problem and I'm like, I don't think this is sufficient. Even still, I'm like, I don't think that's sufficient. And I work through it and I realize, I test the case because that's what I'm going to do. And I realize it is sufficient. And I realize the GMAT is very sneaky. Right. So just know that your gut instinct, it's going to be tricked. That's fine. You want the process to correct it. That's what testing cases is. And we're going to talk today about how that process can go awry, besides just not doing the process at all. So I'm going to give you several questions that I think set up these kinds of issues. So let's just kind of go through them and I'll explain what to keep an eye out for. Take 2 minutes here for this data sufficiency problem. That's 2 minutes. Go ahead and wrap up. So before we go over this, I just want you to go ahead. Yeah, Niraj, good. I see you got the right answer for good reasons. I'm going to tell you all what the answer is. So the answer here is E. I want you to think about whatever letter you chose. And I want you to diagnose what mistake you made. So the right answer is E. What kind of error did you make? Well, it would be a type 1 error of some kind, I suppose. But categorize, okay, so look at the, especially if you chose D, right? You made 2 type 2 errors. So how did that happen? Why did we think these statements, if we did, why did we think these statements were sufficient when they're not? Well, let's kind of go through the process here. So we know M and N are squares of primes, and we know they're different. So we know M is not the same as M. That is important information. And we want to know the value of m minus n, question mark. That's the question. That's what I'm trying to answer. So I have A, D, B, C, E. I go to statement 1. It tells me m times n is 36. Well, okay. It's not a very big number, and m and n are both squares of primes. So let's kind of think about what are the squares of primes, right? I can have 2 squared. By the way, 1 is not prime. A little trivia for you. So 2 squared, 3 squared, 4 squared, 4 is not prime, 5 squared, 6 squared is already 36. So here are the squares of primes I have that fit under 36. And okay, the only 2 that work are 9 and 4. 9 times 4 is 36. So we have our numbers. So 9 and 4. And so, okay, 9 minus 4 is 5. So why 5? Why is that not sufficient? Well, if you think this is sufficient, you might be assuming something that isn't given. Niraj has hit the nail on the head there in the chat. And it's important to think about this up front, to notice this up front. There is no reason to assume that m is the larger number, that m minus n is in fact positive. I could have 9 minus 4 and the answer is 5, or I could have 4 minus 9 and the answer is minus 5. And so if you just kind of assume that it's just usually when we subtract, the bigger number comes first. Negative numbers don't show up in day-to-day life, but they sure do appear on the GMAT. There's nothing here that tells me that I only have positive numbers in everything. I know m and n are going to be positive because they're squares of primes, but there's no reason this has to be positive. So don't assume what's not given. If you do that, you're going to run into problems. That's going to be the same issue with this second statement here. Okay, statement 1 is not sufficient. I get rid of that here. Statement 2 tells me m and n are single digits. And again, they're squares of primes. So same thing, right? Well, m is 4 and n is 9. Those are the only single digit squares of primes, or m is 9 and n is 4. I don't know which is which. So both statements have the exact same issue. Either one could be 4 or 9. So the answer here is E. Neither statement alone is sufficient. So one of the issues to look out for in data sufficiency, especially if you make a type 1 error, is that you've assumed a rule that isn't given. Okay, one of the common mistakes in testing cases. Make sure you're not bringing in an assumption. If it doesn't say integers and there's no reason they have to be integers, don't make them integers. If it can be negative or positive, consider they could be negative. Consider something could be negative. Keep these in mind. Let's try another question here. Talk about another common issue in testing cases. 2 minutes. That is 2 minutes. All right, that's 2:15. Final guesses here. This question, which I did make up, but honestly, it's very similar to a question, one of the official GMAT problems. This one most directly tests how strong your understanding of just the testing cases process is, and how well you just like go through an organized testing cases process. People often, my students often get a general sense of how testing cases works. Oh, I plug in numbers, I test cases, I see what numbers fit the rule and what numbers don't fit the rule. But then when they get into a question like this, where you really have to know the specifics, things go awry. And so the answer to this question, I'll tell you, is B. Statement 2 alone is sufficient. So go ahead and diagnose what kind of error did you make. The right answer is B. So those of you that said C, for instance, that's a type 2 error. You said statement 2 was not sufficient on its own, but it is sufficient. This question, it's also possible to kind of choose A, I think. Some people might choose A, and they'll find that they actually made both a type 1 and a type 2 error. So just go ahead and come back to this one here. Now that you know the answer is B and you know what kind of error you made, I'm going to give you a minute to think about it. Let's see if you can discover where you went awry. All right. If you're at home and you want to keep thinking, hit pause and keep thinking. If you're watching a recording, for those of us here, I'm going to go ahead and lay this one out for us. So we want to know, is X less than 6? Okay. Statement 1 tells us X squared is greater than 36. Well, if you assumed positives, if you made the mistake we just talked about, if you assumed only positive numbers for X, this statement would be sufficient, because you could say like X is 7, and then X squared is, 49 is greater than 36. So you're good to go on the rule. Is X less than 6? No. X is greater than 6. And then you say like, well, okay, what other case is X squared greater than 36? And if you only think of numbers more than 6, you're going to keep getting a no answer. And that's going to feel sufficient, because if you keep getting the same answer in the cases that follow the rule, you've usually proven sufficiency, or at least you can presume sufficiency. And by the way, you can get no answers in a data sufficiency question. It doesn't have to be a yes. Okay. So why is statement 1 insufficient? Well, because you can't assume positives. If I say -10, for instance, -10 squared is 100. Yeah, that's bigger than 36. Is X less than 6? Yes. And this, by the way, this is what proves insufficiency in data sufficiency in testing cases. This is how to prove insufficiency. You find 2 different cases that follow the rules, key idea, follow the rules, but have different answers to the question. And so since I can get 2 cases here that follow the rules, X is 7, X is -10, I've proven insufficiency, because 1 is more than 6 and 1 is less than 6. So A and D are out. Statement 2 is where things get interesting, And if your instinct was like to try to do some classroom algebra here and build a quadratic and factor and all this crud, I don't know. That's, this is not really a high school algebra test. I say that a lot in my classes. Just throw a case down that follows this rule. When is x squared plus 13x less than 42? You don't have to be fancy. And in fact, when you're testing cases, one of the big advice I have is the first case, make it as obvious as possible. Make it as simple and straightforward. Any case that you think will follow the rule, make it stupid simple. So like x is 1 is going to be 1 plus 13. Yeah, that's less than 42. We're good on that. 1 follows the rule. Is x less than 6? Yes, it is. So the question here, now that we have x is 1 and it follows the rule and it's less than 6, the question is, what kind of case should I think of next? What is my goal at this point in the testing cases process? What crosses people up here is they say like, well, if x is 5, 25 plus 13 times 5, 25 plus 65, well, that's not less than 42. That's way bigger than 42. But 5 is less than 6. So I guess this is insufficient because one of the cases follows the rule, but one of them doesn't. And I guess no. When a case breaks a rule, throw it out. That's the key. It's not invited to the party that you're hosting at this data sufficiency question. It doesn't mean anything for sufficient or insufficient. It just means that case is not allowed. The only cases you're allowed to consider are cases that follow the rule. If a case breaks a rule, it doesn't matter what the answer to the question would be. It doesn't matter if x is less than 6 or greater than 6. If it breaks this rule, it doesn't get to come. And you never want to pick a case to see if it breaks a rule. The goal is never really to pick a case that breaks a rule. Your goal is to find 2 cases that follow the rules but get different answers to the question. And so what I should look for after I test 1 and it follows the rule and 1 is less than 6, the thing I want to look for is a no answer, not a no on the rule following, not a no that, not a case that breaks the rule, a case that gets a no answer to the question, meaning a case that is not less than 6. And so, okay, 7, but that's going to break the rule. 49 plus something, that's already not less than 42. 7 breaks the rule, 6 breaks the rule. And so any number more than 6 is not going to follow this rule. And so that means the only numbers that do follow this rule are less than 6. So x must be less than 6. That doesn't mean every number less than 6 follows the rule, but that's not the goal. The goal is, do all the cases that follow the rule have the same answer to the question? Not do all the cases that would have the same answer to the question follow the rule? No, thank you, Joey. Thank you. Yeah, no, thank you for bringing that up. I'm glad you're slowing down. This is a big thing and one of the most common testing cases cross-ups that happens. So it's important we get it. Thank you for asking the question. The question we're dealing with is, do all cases that follow the rule have the same answer to the question? Not, do all cases that would have the same answer to the question follow the rule? If a case breaks a rule, it just doesn't get invited to the party. We want to know, of the cases that are invited to the party, what possible answers are there in those cases? So 1 is invited to the party because 1 squared plus 13, yeah, that's less than 42. Okay. So X could be less than 6. In the case where X is 1, X is less than 6. So I know that's a possible answer to my question. I know it's possible to say, yeah, X is less than 6. Some numbers less than 6 have been invited to this party. I don't know if every number less than 6 has been invited to this party. Don't really care. I just know that some numbers less than 6 have been invited to the party. So the question I now have is, do any numbers more than 6 get invited to this party? Because then I won't know if X is less than 6 or not. If numbers less than 6 and more than 6 are invited to the party, I have insufficiency. But if the only cases invited were less than 6, I have sufficiency. And so I'm wondering, can I make it, is a number more than 6 invited to the party? No way. Every number more than 6 is going to break this rule badly. This rule constrains you enough so that the only cases invited are less than 6. Again, that doesn't mean every case less than 6 is invited, but the ones that are invited are less than 6. And so the answer to this question is B. And this is a huge point, and it's one of the most common mistakes I see in testing cases. It gets people a lot, and they're mixing up the constraint and the question. They're mixing up how to treat the constraints, and they're mixing up what the question means. And you don't want to mix that up. You'll hear me say a lot, case, rule, question, case, rule, question, case, rule, question. Don't mix up which is which. Don't treat one like the other. If the case breaks a rule, it just gets thrown out. If you get a different answer to the question in a case that follows the rule, you've proven insufficiency. So what is the mistake here? This big mistake. When a case breaks a rule, throw it out. No, you got to know what the goal is, which I'll type again. The goal of testing cases. You get 2 cases that follow all rules, but have different answers to the main question. I have my students memorize a sentence a class. And the sentence for class 1 is that. Because I think it's a huge, important thing to lock in and understand. Tell them to put it on a postcard and hang it on their bathroom mirror. You want to have that utterly memorized. All right. Onward and upward. Let's try another question here. Take 2 minutes. All right, it's 2 minutes. Okay. I'm going to let you know the answer here. The answer is once again B. Statement 2 is sufficient and statement 1 is not. So let's go ahead and diagnose your mistake. If the right answer was B, what choice did you choose? I'm going to guess a lot of you either here or in recording land chose D, which means you made a type 1 error about statement 1. You thought it was sufficient when it actually isn't. So I want to, again, pull this back up. Let's look at statement 1 again. Take a minute and look at that statement. If you thought it was sufficient, see if you can figure out why it's not sufficient. Okay, that's a minute. I'm actually here now, kind of wondering if maybe I chose the best example for this mistake. It is a good example, but it's also a little bit in the realm. And by the way, these mistakes we're going from, sometimes they overlap. So this one's a little bit in the realm of, are you assuming something that isn't necessarily given? But I'm going to go ahead and actually, I'm going to give you another question as well. We're just going to jump right to it, and then I'm going to explain how these two both have the same possible trap in them. And I'll explain what that trap is. So take this question here, take 2 minutes, and we'll explain what trap these have in common, what mistake people might make on them. That's 2 minutes. Okay, it's about 2:15. So some of the chats will recognize that they've stepped into the trap on this one. The answer to this question is A. The second statement is not sufficient. So what mistake did you make? If you chose D, well, the right answer is A. You chose D. You made a type 1 error about statement 2. You thought statement 2 was sufficient when it is not. Where was that question? I've lost it. There it is. I'm going to pull this up here with the question I'm about to do. So what do these two questions have in common? This one here and this one here. In order to talk about that, I'm going to talk about a logical fallacy called affirming the consequent. I think. I hope that's what it's called. Big GMAT trap, this one. Affirming the consequence is where if you take something you know is true, for instance, if it's true, if A, then B. If you know that general rule is true, where knowing A lets you know B. The trap is to reverse it, to say that, oh, well, if B, then A. If you know A, then B, you don't always know B, then A. Sometimes it works both ways, but not always. And both of these questions invite the opportunity to step in this bear trap and assume the reverse from pretty commonly tested rules and numbers. This particular error was, I seem to find it most in geometry. I would have done geometry, but pretty soon the GMAT's not going to have geometry on it. For those of you that don't know, the GMAT is changing here at the end of this year. So I decided not to put geometry on here. So this mistake, this kind of error will be a little bit maybe less common, or at least harder to build on their end. It's really easy to set this trap in geometry. Let's talk about how we set it on these two questions here. Well, this question asks, is M an even integer? Some things to notice, right? We don't want to assume things. Notice that we're not told M is an integer. That's just something to notice. You want to notice what's not given so that you're not assuming something. And statement 1 tells us M squared is an even integer. Well, here's the trap. If M is even, then M squared is even. This is true. It does not mean if M squared is even, M is even. Even though it really feels like it should be true. Let's see how we might catch that. Right, certainly M could be 2. And then M squared would be 4, and that follows the rule. And is M even? Yes, it is. So can we get a no? Well, you might have tried it on, you might have tried 3 and then it got 9, but that breaks the rule. Break a rule, throw it out. Any odd integer is going to break the rule, throw it out. You might have tried a fraction. That's also going to break the rule. Like, try 1/4. Well, 1/16 is not an even integer. So we throw it out. Any fraction is going to break the rule. So what number does follow the rule? It gets a different answer to the question. In this case, it might be easier to start at the rule. And then find the case. What do I mean by that? Well, M squared is an even integer. So let's just make M squared an even integer. 2. If M squared is 2, that follows the rule because that's an even integer for M squared. What would M be? The square root of 2. Very annoying. But technically allowed. So is M an even integer? Not if it's the square root of 2. Square root of 2 follows the rule because M squared is even. 2 follows the rule because 2 squared is even. One of them, M is an even integer. One of them, M is not an even integer. So statement 1 is not sufficient. But it's so easy to slip into logic like this. It's also easy to forget about your square roots. Statement 2 tells me square root of M is even, and this is going to be sufficient. Once again, we have a B answer. because what numbers follow this rule? Well, perfect squares that are even, like 4. Then square root of m is 2. Is m even? Yes. And then, okay, 6, square root of 6 is not an even integer, throw it out. Any odd number, 25, 5 is not an even integer, throw it out. You're only going to work with perfect squares. And those keep m as an even integer. So the answer to this one is B. How did that next question invite the opportunity to affirm the consequent? Well, we have this set of numbers up front. We have, oh, that's not the problem we did. Is that the problem we did? I hope it's not. I meant to do this problem. This is the problem we did, right? It was these numbers. Okay, good. Yeah. So we have these numbers. So first thing to do, put them in order, right? We have the numbers 5, 7, 9, 13. And then there's this X floating somewhere. We don't know where it is, but it's in the set. And we want to know the median in the set. And we do know X is an integer. That's nice. They told us, hey, we only have integers here. Don't worry about fractions or decimals. Technically, it doesn't say X is positive, but I think that's all. We're not going to have to worry about negatives. We want to know the median. Well, I actually think this is a good example also of a time where we might do a little pre-phrasing. Let's think about where X could be and what the medians could be, right? I could put X to the left of 9, excuse me, to the left of 7. And maybe it's, it could also be 6, but if X is left of 7, the median is 7. If X is more than 9, 9X and 13. And again, X could be more than 13, but the median would be 9 if X is more than 9. X is less than 7. X is more than 9. The other chance is that X is the median. So I have like 5, 7, X, 9, and 13. Probably be 8 in that case. So these are the 3 worlds that I'm dealing with where I'm trying to figure out the median. The median is either 7 or 9 or X. Statement 1 tells me X is greater than 9. So that immediately puts me into that case here. If X is greater than 9, then the median is 9. There's not a lot of cases to test other than that. If you want to test a few to prove it, you're going to find the median is 9 in every case. So statement 1 is definitely sufficient. It's either A or D. It was the second statement that sets the trap, where the median equals the mean. And if you've done some GMAT study, you actually know there's a rule that's very handy to keep in mind, and the GMAT does want you to know. If a set is evenly spaced, the median equals the mean. What do we mean by evenly spaced? We mean, same increments between numbers. And it's like, oh man, I can already tell this set is almost evenly spaced. If X is 11, I have 5, 7, 9, 11, 13. I know that's a case where the median equals the mean, and the median would be 9. And if you think, well, great, that's when the median equals the mean, when the set is perfectly balanced, or when the set is evenly spaced. I don't need to test anything else. You stepped into the trap. If a set, this does not mean, if a set is evenly spaced, the median equals the mean, does not mean, sorry to use that word twice, but this does not equal when the median equals the mean, the set is necessarily evenly spaced. That's affirming the consequent. There are other sets where the median can equal the mean. And that's what your job is. You have to think about that now. You have to actually say, like, okay, I know the median could be 9 and the set could be evenly spaced. but could I make the median 07? Right? Can I make this set possible where the mean equals the median, where the mean is also 7? So we're going to have to do a little bit of algebra here to work this out, but let's see if we can solve for x if the mean is 7 and make sure that the median is also 7. Well, the sum of the numbers we have is 5, 12, 21, 34. So 34 plus x over my 5 numbers needs to get me 7. That means x is going to be 1. And so if x is 1, yeah, the median would be 7. The mean would be 7 because that's what I solved for. And I have 2 different cases that follow the rule. And so I have to choose A. That's a type 1 error caused by probably affirming the consequent, assuming that this must be true because this is true. You got to be careful. You got to know which way logic flows. Sometimes it flows both ways, right? If x is 4, then x cubed is 64. And that logic flows both ways. If x cubed is 64, x is 4. That logic flows both ways. If x is 4, x squared is 16. That logic doesn't flow both ways. If x squared is 16, x might be negative 4. And if they don't tell you x is positive, you have to be aware of that possibility. So make sure that the logic flows both ways. And if you're unsure, think about how you could test a case. See if you can make the median 7 and still fall, and solve for what x would be. All you got to do is do it. It's not hard once you do it. You're just like, I got to see if the median could be 7. Well, what's x when the average is 7? Well, it's 34 plus x over 5 is 7. Oh, well, then 34 plus x is 35. X would be 1. If x is 1, yeah, the median is 7. The average, you just have to have the habit to do it. Doing it is not the hard part. The realization to do it is tricky. You have to check your gut impulses here and actually test all the cases. All right. So don't affirm the consequent. Be on the lookout for it. And yeah, Niraj, I think pre-thinking is very helpful in this situation to lay out what the possible medians are ahead of time so that you have them kind of ready to test. Could the median be 9? Sure, that's perfectly balanced set. Could the median be 7? Well, I've already thought that that's possible up front. So what if it's 7? Well, then what would x be? Okay, it'd be 1. Yep, that works. We're good to go. Let's try another question about sets here. Take 2 minutes. Hey, that is 2 minutes. So I'm going to say that the answer to this question is D. Each statement alone is sufficient. So let's take a look here. If the right answer is D, what did you choose? I think the most common choice here is or the most common wrong answer choice is probably going to be A, saying that statement 1 is sufficient and statement 2 is not. Statement 2 is. So if you made that mistake, or if you're wondering how someone might make this mistake, let's take a look at this question. I have my setup here. Statement 1 tells me that the sum of the 5 numbers is 160. You probably can just do your average equation, say, well, okay, if the sum is 160, the average is 160 divided by 5, which is greater than 30. It's going to be 32. And so is the average greater than 30? Yep. I don't have to test any other case. We're already good to go. So it's either A or D. B, C, and E are out. Statement 2 is the trap, and there's a few things that might lead you to say statement 2 is insufficient. I think the first is that statement 2 feels kind of vague. It just feels like each integer is a multiple of 10, but I have no idea. There's so many sets of multiples of 10. How am I supposed to know if the average is at least 30 when who knows how many multiples of 10 there are? Well, this is in the family of not testing cases when you should, right? Yeah, maybe you're right. Maybe there are so many possible sets of multiples of 10 that you don't have sufficiency, but prove it. Build some sets that actually have, so start easy, right? What's the 10, 20, 30, 40, 50? 5 consecutive integers. Is the average greater than 30, greater than or equal to 30? Because it says at least 30. Yeah, because there the average of the set is 30. And so again, what should I think of now? I should think of a set where the average is actually less than 30. I already know it's possible to have an average that is at least 30. There's a lot of other cases where that's going to work as well. My question is, can I make an average where a set where the average is less than 30? And we're going to run into a few problems here, but there might have been some things you did, right? Maybe the first thing you did was like, well, what if it's negatives? What is, negative 50, negative 40, negative 30, negative 20, negative 10, all those negative numbers. Well, then the average would be less than 0 even, but they tell us it's positive. I didn't even write that down. We have to know that they're positive integers here. It also says they have to be different. So I can't do like 10, 10, 10, 10, 10. I have to have 10 different positive multiples of 10. 5 different positive multiples of 10. This is actually the smallest possible set of the constraints. Any other set is going to have a bigger average. And so the average is always going to be at least 30. And so the answer here is D. So you have to be careful here. There's 2 mistakes that cause people to say statement 2 is not sufficient. Either you just didn't test the case. You just thought like, there's so many cases. There's so many cases that I know follow that rule. Who knows what the answer is? You have to check to make sure that the possible cases actually have different answers. Many times there are infinite possible cases in a problem, but they all have the same answer. And that's the case here. There are infinite sets that I could build. They're each multiples of 10. They're each positive and they're each different. I could build a lot of sets like that, but every one of them under these constraints has an average of at least 30. So make sure you actually get to different answers, not just different sets. And then make sure you didn't overlook a constraint. If you don't notice that these are positive integers, and if you didn't notice they're different positive integers, you might say, oh, let's make them all 10, because then the average would be less than 10 or less than 30. Or you might say, let's make them negative. Well, then the average would be less than 30. You can't make them negative. You can't make them all 10. Make sure you catch the constraints. All right, those are big ones. Let's do one more and then we'll wrap up for the night. Take 2 minutes for this data sufficiency problem. Right, that's 2 minutes. So the answer to this question is once again B. I didn't mean to have so many B answers tonight, but there we are. We have another answer of B. So diagnose, if you chose A or D, see if you can figure out what happened, or C, what mistake did you make? We know A and B are positive integers. We want to know, is B even? Statement 1 tells me AB plus B is even. And so let's kind of think about a situation, right? Let's say B is even. That's a case. You don't actually have to test, you can test numbers, or you can just test kinds of numbers in this instance. So if B is even, A times B is even, plus an even number is even. So B could be even. Is B even? Yes. So the question is, can we make B odd? Well, then we'll have plus an odd, because B will be odd. And we need this to be even. So we need to add an odd at the beginning. We need an odd plus an odd in this case. So that means A also has to be odd. And there's no reason A can't be odd necessarily. But you might be wondering, like, is A odd or not? Because if A is odd, B is odd. But if A is even, B would have to be even for statement 1's rule. So you might have had that realization for statement 1, like, if B has to be even if A is even in statement 1. So is A even? That's the question. Statement 2 comes around and says A times B is odd. We know statement 1 is not sufficient, so A and D are gone. Then we look at statement 2 and it says A times B is odd. And if you clung too much to that question, is A even or not? Then this tells us A is odd. You might jump too quickly to say C. You might say, B gives me the piece of information I needed for statement 1, because if A is odd, B must be even. So statement 1 and statement 2 together would be sufficient. But that's rush. First, you're bleeding the statements together too much, and you're not fully treating statement 2 on its own. And you actually need to realize that B also must be odd for this statement 2 to work. So is B even? No. Could B be even? No, it breaks the rule. So throw it out. B has to be odd in statement 2, so the answer is B. Statement 2 alone is sufficient. This is just a general data. Honestly, this is not really specific to testing cases. It's just a general data sufficiency thing. Don't let your statements bleed too much. Make sure you thoroughly treat them each on their own before you bring them together. It's easy sometimes to do some good work on statement one and to realize that, realize something about statement one, and then, oh, statement two gives me that piece of information I needed. So statement one, now I have it. Now it's C, but you didn't take statement two on its own first. Maybe statement two actually has everything you need on its own. Don't let your statements bleed too much. Just for fun, I'm going to give you some other questions we didn't get to tonight that if you want to pause the video and work on them, you can. Those of you that are here, you can just take a screenshot. Okay. Here is a question that I think is a good testing cases example. So take a screenshot or pause the video. I'm going to write the answer in a moment. So if you're here and you want to do this later without knowing the answer, close your eyes. Ready, set, close your eyes. This is the answer to that question. You can open your eyes if you're here. Check. Okay, so if you did that question, if you pause the video and did that question, you know the answer now. What answer did you choose? Where do you think you might have overlooked something? This is a Manhattan Prep classic. We've done this one a lot in several videos, but it's always worth redoing. Try it again. Or if you've never done it, try it a first time. Or, if you're watching the video, pause and try it. If you're here, take a screenshot. And I'm going to show you the answer in 5, 4, 3, 2, 1. Cover your eyes if you don't want to know. That is the answer to this question. Gauge your answer to that answer. See what kind of mistake you made. Here's another one. Take a screenshot if you're here. If you're home, pause it and try it. I gotta make sure I got this one right. I want to make sure I haven't made a mistake. Yes, okay. So I'm going to show the answer in 3, 2, 1. That is the answer to this one. Okay. And yeah, I'd say this one's also a good one here. This one here, take a screenshot if you're here. If you're at home, hit pause and give it a try. I'm going to write the answer in 5, 4, 3, 2, 1. That's the answer to this one. Analyze your answer and see what mistake you made. These are the common mistakes that cause type 1 errors and type 2 errors. If you found yourself making one of these errors, see if you can diagnose which mistake you made. Develop the habits that will help avoid that mistake. It's pretty systematic in this way. I'm not saying these are the only ones to make, but these are very, very common. So check, see, and the GMAT is setting up for these common kinds of mistakes. So check and see what your process led you to. Thank you all for attending tonight, and thank you for watching the recording. For those of you that watched it on YouTube, check out our courses coming up. Attend some of the free prep hours, or the free foundations of math, or the free first class of a course. We hope to see you there. Otherwise, we will see you here next time. Thanks for coming. Happy studying.